I mean, starting off, was there any question on the linear power supplies that we went over last week? Nothing you're doing. So we're basically building off of that into the next power supply style being the switch mode, which I can break down in a similar way to see how it can behave similar to it can be represented similar to the linear supply that we saw last time. But jumping into it, for the switch mode power supplies that we'll be looking at, there's two major ones. Buck converter and boost converter. These are the two major switch mode supplies. There are others like a buck boost and such. I'm not going to touch on those because they're not as commonly used for us. Main focus, what we deal with is buck converters. For one, the buck converter is a step down, while a boost converter is a step up. That is, for the buck, you'll give it some input voltage and just drop it to a lower, much like how we saw for linear supplies. It'll take some voltage and just bring it down to a lower voltage to be used. While boost will have some V in and it'll step it up to a higher voltage range. So you can supply it with 5 volts and you'll get 12 volts on the output. So this is where you start to see more use of a switch mode compared to a linear supply. If you only have 5 volts available, but you have to supply something with, if you have to power something with 12 volts, you have to use something like a boost converter. In our car, we don't have a use for a boost converter, simply because all the circuits we work with are 12 volts or lower. And since we have a 168 volt battery pack, anything that may need slightly more, it's a lot easier to tap in from that and have it step down than it is to take our already step down 12 and then boost it back up. But it works out in our case that none of our circuits require greater than 12 volts, other than the high voltage ones. So for the most case, we just require the buck, and we see that in a couple of our boards. Yeah.
What happens to the current in both of those cases?
There's a couple different in a buck converter. You can get a higher current draw than from your input, while the boost you can only go down, because in simplest form, power in roughly equals power out, with the exception of losses. So if you're pumping in for say $1, 12 volt at 1 amp, and now on the output you have 5 volts, the power, you're still able to achieve a similar power, so your current can increase. And then the opposite is true for a boost. If you're giving 12 volts 1 amp, and then all of a sudden you boost it up to 20 volts, you have less current available. And then within each converter, there's different current modes that they can be in, depending on how much your load is trying to draw from it. And I'll touch on that a little bit as well to see how those behave when you try to pull more than you're actually able to supply. Any other questions just on the start of either buck boost?
How high can it boost up?
So how high can we boost up? Theoretically, you can go. That's a good question. Theoretically, I believe you would. There's technically no limit, as long as you have appropriately spec'd components. But the problem is, if you are starting at 12 volts, 1 amp, and then you try to bring it to 200 volts, you're going to have micro amps. Like you're going to have nothing useful in that case. And to do this, all of your components have to be much more suitably rated for the voltage applied. But I think theoretically there is no upper limit. There's just more efficient ways if you want to go higher voltage.
Okay. Well.
There was something in chat. What's the reason for using a buck opposed to a voltage divider? Efficiency. So we'll see in a minute when I start showing the operation of a buck. But in simplest, if we have a voltage divider, and we're again just trying to go 12 volts down to 5 volts, you are constantly just bleeding off power through these resistors. Since you are pushing a current through the resistors, power, current, and voltage, you're going to have some heat losses due to this conversion. Where as a buck, we're being a switch mode supply. It's instead of constantly bleeding power through a resistor or any of the other passive components, it's instead turning it on and off very rapidly, so that it's not just wasting its energy away through passive components or any other components for that matter.
And also the voltage is more stable when you have fluctuating current demands.
Yeah, yeah, that's one of the other things is you can see much more voltage sags on something like this compared to the switch mode. Anything else before we jump right into the buck? So yeah, starting off with the buck converter, the typical design. So made up of basically all of the passive components that we saw before. And then this goes out to our load, plus minus. And then this is our input. So commonly you'll just see your battery connected to it. Our N-channel MOSFET that connects to some gate driver. So what we'll see is we'll be able to supply our 12 volts in, see our 5 volts out on the load. And how this is achieved is heavily dependent on our MOSFET being whether we have it active or not. If active or not. So if we're sending a 1, if we're sending 3 volt, 5 volt, whatever our turn on voltage is for a MOSFET, what we'll see is current is allowed to flow through. We'll discuss what happens on the inductor. But as we remember, it was that inductors don't like instantaneous changes in voltage. Current. No, it's voltage, right?
Current.
Yeah, that's right. So there's going to be a minor delay in the current voltage relation at this point before it becomes fully charged. But where that power's able to come through, go through the load, and then it's got its return path to ground. So our current path when our MOSFET is active is very simply from battery across the inductor through the load, and then back return path to ground. And in the case when we are now turned off, current can't flow through our MOSFET, but we have 2 energy storage devices in the system. One that stores as our magnetic, and then one that stores our static voltages, static charges. So we have 2 energy storage devices. And as we saw when we went over inductors and capacitors, how they don't like instantaneous changes in current and voltage. Having the two together is what basically balance out each other. So if you were to only have an inductor in the system and no capacitor, if the capacitor was just out or is it just a resistor, when you switch it on and off, because this is for an inductor, what we see with an inductor is a high voltage spike and slow current. And then if we were to turn it off, it goes slow current and then a sharp voltage spike. So if we only had the inductor in our system, whenever we switch our MOSFET on and off, we would constantly see massive spikes in voltage, which would basically, no question, damage your whatever is on your load. Assuming that it doesn't have, if you're only wanting to send it 5 volts, it probably can't handle whatever plus 20 volts that you may be seeing, plus minus 20 volts that you may be seeing spike. And then quite opposite for the, or inversely as the capacitor, that slow voltage, but it has big current spikes. Again, the current spikes would be most likely damaging to the devices or what is ever on your load. So by having these two in the system together, they're basically able to absorb each other's spikes, such that nothing in the system will get damaged when we're switching our MOSFET on and off so rapidly. We won't hit massive spikes, and the voltage current growth will be relatively smooth throughout. But if we now, so when we see that, we now say we send our 0. So we're blocking, but we have stored charge. Our current path now comes up through the flyback diode, and we have a small current path just between the storage devices and our diode. Can anybody tell me why our current path when we're turned on is through the diode? Why this is only active in our 0 state, our MOSFET off state? Anybody?
I think like when the MOSFET got off, so like we have the capacitor to store the charge, and then like so we have the diode, so like the current has to flow through the diode, so that's why we have like that. No.
Yeah, and then what's not making the current go through this path when we're turned on? Nobody? A little easier than that.
It's not a trick question.
It's jumping right back to how a diode behaves. If you can remember back onto that lesson. What we see is diodes only want to allow current flow in one direction and block in the opposite. Now, in the case of what we have in our scenario here, this node is tied to the negative pole, so this node is tied to ground, while this is tied zero volt or 0 volt 12 volt. Current wants to flow from positive to ground, but our diode is blocking it. So it's essentially wanting to come down, but our diode is here, blocks it. So its only path is to continue through the rest of the system. Nothing tricky about it, just the blocking operation that is a diode. What was the question originally? Why is there no current flow in this path when our MOSFET is turned on? Yes, that path. But yeah, it's a simple current flow. Yeah, no, only about that path for the on section. Yeah, any questions on kind of the current paths in general so far? Makes sense to where current is flowing, why current is flowing in our on and off state. Okay. So to jump into, to kind of relate this back to the linear regulator that we saw last, which was inputs so this was our linear regulator last time. What we see is now we go outside of the circuit. We see our extra components for the energy storage. That's a terrible vector. And then internally, what we saw before was the op amp directly connected to our transistor base. We're swapping this out for N-channel MOSFET now. Most N-channel MOSFET compared to transistor more is a power reason. But we saw last time having this direct connection isn't going to be the most efficient because it's always going to be drawing power to just keep that cycle going. What is happening here instead is the op amp is more um, controlling a switch to power. So our op amp is actually toggling a switch internally. This is more just about what a gate driver is doing in general. But we can see that in the base of it, a linear regulator compared to a switch mode can be represented as a fairly similar system, where the primary difference being your external circuitry, and then internal to the device being, instead of just an op amp driving directly, you're driving basically you're driving a switch. So the power isn't constantly being run through this path. This is just a quick kind of how you can semi-relate it to the linear regulator. It's not often shown like this because this is a little more deep dive than anybody ever actually cares about for buck converters, but just so you have a kind of reference to how a switch mode ties closely to a linear.
One interesting note is usually for the switch mode power supplies, that set of feedback resistors is usually at the very end, so that it gets like a good representation of what the output is actually doing.
Yeah, all the way to what your actual load would be seeing.
Yeah.
Yeah, because the voltage at this point isn't quite accurate to what your output voltage is going to be. But yeah, quick how that ties together. But for what really matters is our gate driver just being some form of a square wave, just toggling on and off. That's being state to the gate to turn on and off repeatedly. Now, how we're able to accomplish stepping down by doing all of this is dependent on our duty cycle. So what we get is we send some duty cycle, say 50%, of the whatever required threshold voltage. Just say we send 5 volts of a nice square wave of 50% on for 50% off. What that relates to is, again, if we have 12 volts in, what we get is our output voltage, so what we get to the load, is just going to be our input by our duty cycle. So in this case, what we'll get is we will see 6 volts on our output in this case. This is assuming the continuous current mode which is the ideal state of a buck. But when it's in this ideal range of drawing only what it actually wants to see, it's just as simple as your output is just going to be whatever duty cycle multiplied by your input. Now, what does this look like? I don't have. Yeah, so this. And then what we will see is our output current is going to be related to the current of our inductor. So this, because we saw the behavior of the inductor doesn't like instant current, so it's got slow rise and fall times of our current. What we get here is our current will slowly rise, slowly fall, slowly rise. So our output current is going to have this kind of ripple, or it's going to be more following the curve a little bit better. But it's going to have this ripple waveform to it because of the inductor's behavior of not liking to switch. So we'll see a minor ripple. This is typically a fairly low variation. So it's not like this is going to be pulling half an amp and then peak at 1 amp. Like it's a fairly minimal variation, a small waveform of what the actual current output is. I do have an equation for that somewhere. Yeah, so there is what is this? Forgot how much actual equations I have on these. But we can see our let's jump into the two kind of modes that we can see. Like I kind of mentioned, there's continuous current mode and discontinuous. So these modes that the device can operate in is dependent on the current waveform, how we can see its behavior being a little bit choppy, and how that behaves with what our load is trying to draw. Like we said at the beginning, we can get a slightly higher current output from our input, so we will have a higher current limit than normally, but um, if that's 0 amps, our CCM, DCM is how they're typically called, or how they're denoted as. Continuous current mode is getting the current draw to be what we saw, just this waveform up in the acceptable, some amount of current range. Assume our system is able to draw our system is only able to draw 50 milliamps. We're only driving a couple LEDs, and our buck converter layout is capable of outputting 1 amp. We will very easily see that we have, and the ripple will stay within the acceptable range. But now let's say we're trying to draw something a little heavier. Maybe, again, our converter's only able to source 1 amp of current, but we're trying to drive something a little heavier, maybe a very weak motor, and it requires 1.5 amps. What we can see is our waveform basically dipping below 0 amps, which obviously is not a achievable scenario. So our waveform gets chopped. So at points we're sending no power. This is what will happen when you try to draw something heavier than what you can supply. Basically, it's demanding more current than you can supply it. So your system will just end up chopping it, and you're not able to achieve the same power output. When the DCM, the discontinuous mode occurs, your output voltage also then changes because you're now no longer able to supply the same power. Your voltage levels, your current levels change drastically. Yeah, I could go through all of those equations. Yeah, so our output current average. So again, if we are just to assume this isn't rippling too much, and we have some average current value coming out of this. Our average this is the value that kind of defines whether we're okay. And it's dependent on the inductor that we have, because that is the device that is limiting the current in our system. That's causing the slow buildup and fall. So that is what's directly affecting any current consumption in our system, alongside what our expected input output buyer duty and our switching period, how fast we're actually turning on and off our MOSFET. So basically, this is what your average output of the system will be. And depending on if your load is trying to draw more or less than what we can actually hit, what changes your conditions from being continuous or discontinuous. Questions on this stuff so far? I know I'm not explaining it the best.
Is that and then the bottom one? Is that all an equation? Is it all multiplied?
Yeah, so this is whatever.
Ah, okay. Thank you.
Any other questions on the continuous and discontinuous?
Application wise, what's the difference between CCM and DCM? Like, what would it look like to our output? When would you use it?
You basically always want to be in continuous mode, because that is proper operation. You're supplying the simple whatever output is just being a function of your duty cycle to your input. Current is the whatever level you need it. It's exactly as you want it to be. I shouldn't say you don't. You basically don't want to be running in the discontinuous mode. I'm sure. Yeah, I don't believe there's actually a proper application where you would want to be running in DCM, from my memory. Because it is basically running in a system where you're not able to deliver enough power, so it's not going to be doing as it's intended to do.
Will a certain load make the buck converter make a buck converter run in DCM?
Yeah, because
what does that look like?
You'll design, because you'll design this around one application, or for you'll say I want 5 volts and the ability to do 3 amps, and so that's the range you always want to run. But yeah, it's very easy to give it a different load that once is more demanding, and it will cause it to fall into that DCM mode. But you basically want to avoid that, because then you're not able to send it adequate power. Like I said, when you're in your DCM, you're no longer sending the nice output voltage. Instead, you got some bullshit of input, and it's going to be your duty cycle squared. You guys will see this if you're taking MSE 353 at whatever point that is. Yeah, so you now run into this being your output voltage, a lot more dependent on, you're now more on whatever, and then again you would sub this in, so it becomes a lot more of a mess, and you are basically not able to achieve the same outputs as you are intending. I mean, maybe Gabe knows better if there is an application of wanting to run in DC. But from what I know, you basically want to avoid this whenever you can. Gabe, any input?
I've never wanted to per se. Usually it's because the energy in your inductor has run out, so you can't keep supplying current within that period. So I've never purposefully tried, but I'm also not like a power electronics expert. From like a quick Google, some people say that you can use it if you want to be very clever with like the power factor that you're creating. So like the waveform quality you have. So quick, okay. Pros and cons. Continuous current mode, the voltage gain is not dependent on the load. The input current is continuous and not pulsating, yeah. The ripple component of the inductor is lower, and higher efficiencies can be achieved. In discontinuous mode, the gain depends on the load, so you don't have that simple duty cycle times input anymore, right? You have all this crap. The ripple is higher, and apparently the size of the inductor, if you only run in DCM, you could use a smaller inductor if that's what you want, because your inductor won't have to be as big to keep supplying energy within the period, but you do have that pulsating current. So I've always tried to use CCM, and to be honest, like with the buck converters I've used before, I'm not monitoring the current actively, so I haven't actually noticed if any of them switch into DCM. So I'm pretty oblivious.
Yeah, I mean, from my understanding as well, you don't want to be in DCM because it just causes more problems away from delivering the power that you're actually intending to supply.
Yeah, and unless you're actually designing the buck converter yourself, you're probably not going to have to worry about this. But if you were creating like a buck converter controller, then it'd be something to watch out for.
Yeah, I've never given it significant thought in all the things I've done related to that.
Yeah, I don't know if that's an oversight on our part or if that's like just well designed from whoever made them so that you won't really notice. But yeah,
I mean, usually when they switch, they do so pretty well, especially the more modern ones, and they even have like high efficiency modes at really low current draw.
Yeah, that's a good point. Some of them they'll say in their data sheet like light load operation sometimes, or like they'll have a minimum load because underneath that load they're not guaranteed to output a very good waveform. So sometimes you have to at least guarantee that load. And I remember a long time ago, back in the go-kart, we used I think a buck converter that had like a minimum 10 milliamp load. So if you were drawing less than 10 milliamps, it said it was going to enter DCM, and there were no guarantees anymore. So like we literally had to just put a resistor on the output of that buck converter that would burn 10 milliamps always to keep it in the right operation, the right operating mode. But I think now buck converters are usually decent enough that they're able to either do no load or light load, and maybe they just lose a little bit of efficiency. But it's common to have some sort of qualifier for light load operation where you have very minimal current draw.
Yeah. So another kind of way of redrawing this current waveform is if we're just looking at the current across our inductor. Like we are starting from nothing, so it's a slow build up and then slow decline. That'd be its normal operation if we were to switch it slow enough for it to do its full discharge rates. But as we, so this is some very slow switching. So that's the running light loads. You can easily hit that DCM mode when you're doing slow switching, because you get to the point where it has, no power left to give. So as you're trying to draw that, you're very easily able to hit DCM. As you increase your switching speed, so we get up there, and then we turn it off, and then we instantly turn it back on, so it rises, and then we keep switching up here. This is now where it wants to be. So this is going to be your faster switching, and whatever it may be, depending on your inductor value, maybe that's your 50% switching. And then if we were to say just turn our MOSFET on and leave it on, you're just going to tap out at the current range, and you're always going to be supplying 100%. This is also not an ideal case or depending on your application. For the sake of stepping down a voltage, this obviously doesn't work worth anything, because you're gonna, again, being by your duty. And if you have 100% duty cycle, your output's just gonna be your input. So you'll just see 12 volts across, current will be whatever it is on the inductor. But we can see as we increase our switching speed, or our duty cycle rather, switching period is the proper, our current waveform becomes more and more steady, more ideal, and less likely to dip into discontinuous mode, purely based off of switching speed. We're still able to have the problem where our load tries to draw more than we can supply. So even doing it at 100%, our load still may want more than this amount of current, which will cause the discontinuous problems again. So we can still hit it, but as we increase our switching speed, it becomes a lot more stable, and we have a higher current output capable with less ripple. So that's the current, so those are the two modes. Again, want to avoid DCM when we can. We want a smoother ripple form for both input and output. Because again, because we have our capacitor in the system, basically directly tied with the parallel to our output, and capacitors are slow, or they resist the change of voltage, because this is our volt. Our where am I? Our output voltage is also going to look slightly rippled, just like how our inductor is causing these little ripples. The capacitor is doing the same thing, since it is taking, when we initially switch on the device, so we allow current to flow, some current, some voltage builds up in the capacitor before it becomes fully charged, and in that case, we come across, and then as we are switching our device, our MOSFET open, it's going to have that same, slow decline. So our voltage is also going to have a bit of a ripple to it. So our current waveform is going to look like this, and our voltage across the capacitor, which is our output, is going to look fairly similar, where it doesn't like that change, and then it's also going to have that little bit of a ripple. Again, it's typically a low bandwidth of amplitude on the ripples. I think the typical, I believe the typical is 1% ripple. So if we're trying to hold a steady 5 volts, the allowable, or the desired ripple that we kind of try to design around, is plus minus 1%. So again, you're only going to have whatever that is. Milliamps of ripple. So I believe similar. The current has a slightly larger ripple to it, because that is more dependent on the demand of the load. So you'll see much more fluctuations on your current waveform compared to your voltage waveform. Your voltage should be able to stay constant within this 1% range fairly consistently throughout the operation until it falls into the discontinuous mode, in which case you'll see sags and all the problems that come with being in the discontinuous mode. And to design for this 1%, what we can do, so if we want to reduce our voltage ripple, what you can do is decrease your corner frequency. This can be done by increasing either inductance or capacitance. Because again, based on the behavior of not liking changes in volt and current, and then each creating their own spike in voltage and current, respectively. They can, by increasing either, you're basically able to absorb those transients a lot better. So if you have a larger capacitance, you're better able to resist such high spikes that come with. That will be a result of our inductor. Because again, get out of here. Going back to the inductor capacitor lessons that we did, our corner frequency or back to the, I guess, filters lessons is when we looked at this relation. So we can play with both of these values to be able to decrease that corner frequency, basically suppress those transients as much as we can. Because again, like we mentioned on how square waves aren't just square waves. They like to have these overshoots and undershoots on the rising and falling edges. These are known as the corner frequencies. So playing with either your inductor or capacitance, increasing them, we're able to suppress these, which are a cause of our voltage ripple on our output. Other things we can do is increase the switching frequency. So this is to say, basically, if instead of running this at 1 kilohertz, boost it up, run it at 10 kilohertz. It'll help with decreasing the voltage ripple, but in turn will have increased switching losses. As well as decreased efficiency. So it's less ideal to run it, to have this as your primary way of reducing ripple. Just by increasing, you add a few more losses into the system. So it shouldn't be the go-to way to get rid of that ripple.
But by increasing that switching frequency, aren't you making those overshoot spikes on the switch itself much larger?
Yes.
Like the transients you're showing in red.
Yeah.
Those would be increased. Which I suppose isn't like noise on your output voltage ripple, but it is still noise, a high frequency noise introduced into your system.
Yes. these are wonderful notes because this is straight from 353. These aren't things we questioned.
I know. Things like also efficiency. I've noticed even the high frequency switching devices tend to be pretty up there with efficiency compared to like lower frequency parts.
Yeah, you're able to get high efficiency. Like if your device is rated 100 kilohertz plus, we're still able to achieve similar, whatever, 85 to 95% efficiency, whatever it be, similar to a device that only switches at not 1 hertz, it's 1 kilohertz. It's just that all the devices in the system have to be designed to handle such a high switching frequency. Like your MOSFET would be spec'd differently in the two applications based off of recovery time and like gate charges and everything, such that it can actually properly turn on and off at that speed without having that extra transient still remaining on the gate. So if the device is properly spec'd to be switching at that, it's more than capable of hitting the same efficiency. It's more when you have a device set for one thing and your go-to is to try increasing its switching frequency, is when you'll see efficiency drop. Any other comments on the buck, on everything?
What's the limit on filtering your output? Like if you're increasing your inductor and capacitor values, what point is it sufficiently filtered?
It's typically considered good enough when your change in your output voltage or your output voltage is less than 1%. So that's the kind of bullshit that I was saying. If you have a 5-volt output, basically once your ripple is sub 1%, I believe that's the considered good enough. So that's that shit. So if we were to say this is 5 volts, as long as that ripple is plus minus 5 milliamp, that's when we that's when we call it good enough. Okay, we're at just over an hour now. This is everything I had for the buck converter. Do you guys want to carry on to boost right now, or should that be saved?
I mean, how much you got on boost? Can't be that much, right?
It's yeah, like the boost is going to be a little bit less since, went over basics of how things are operating. But probably half hour at least. Up to you guys.
I'm fine with going over boost right now.
Everybody else?
I'm okay with it because it's alright. Like they're kind of hand in hand. But I don't know about other guys. But the new people, this might be a little overwhelming.
If they're not going to speak up,
Probably not today, because I had 2 midterms today. I just don't know if I can digest all this information.
That's fair. But the buck itself was a lot of information.
yeah. Okay. We can hold off on the boost converter. We'll touch on that next week. So yeah, we'll stop it at the buck converter. But since we're stopping it there, I'm going to require 3 questions before we actually quit.
Damn.
Gabe, what have you done?
You've influenced him.
Yeah, next week I'll start asking about your favorite colors.
No, favorite ice cream flavor. Don't steal Gabe. You already answered those questions. You have to have your unique questions.
Yes. Yes. So
Like a Rocky Road or something. No.
yeah. So okay, quitting at buck. 3 questions. Someone who hasn't said something, preferably. Paulina, Raphael, Brayden, any questions on anything?
Yeah, so I actually had a question going back a little bit. When you first, in your first buck diagram, when there was, you were talking about a different loop when the system's off. So like the loop through the inductor, capacitor, and diode. Why does that, like the blue loop?
Yes.
Why does that only happen when you're sending a 0, not a 1?
Yeah. So let's just redraw that because that one's a mess. So we have. Let's make it easier. It's a switch. So when our switch is closed, we get that the current flow is straight across everything. Because because of the diode connection, it sees 12 volts and 0 volts. So it blocks. So our current path has to be throughout the rest of the system. However, once we open it, so this is setting a 0 to the gate, this is sending a 1 to the gate. We have built up static charge in our capacitor and magnetic charge in our inductor. So now that we have taken away the power source to the system, there's nothing left in this loop, and then it goes out. There's nothing left in this system to be supplying power to these devices. They're now able to discharge the power that they had remaining. So we're now able to see that they release theirs as they discharge, and because we're now disconnected from this half, we're no longer seeing the 12 volts and 0 volts across the diode as we were before. So we're allowing current flow to happen through our devices.
Oh, okay. Got that. Thank you.
I thought there's no DC current flow through capacitors.
There distinctly is because of switching. It looks like AC.
I think the cap is sourcing current, and the current flows through the load.
Yeah, because this isn't just a cutoff system that has nothing to it. This is going to some load, so these current paths are actually going through the actual load. Because since this isn't a closed system, the actual power path is through the load. Another question.
Yeah, can you summarize like what the switching frequency mainly determines?
Yeah, so or the switching frequency or the switching period. Because yeah, so there's two things about I guess about it. So yeah, we're always just sending some square wave to the gate. Now, if we send a low duty cycle, whatever, 10%, your output voltage is going to be 10% of your input voltage. And then opposite, if you're sending say 90%, your output voltage will be 90% of whatever your input voltage was. So by changing your switching period or your duty cycle, basically how long you're sending either a 1 or a 0 will determine what your output voltage will be. And then changing the actual switching frequency. So if you go from a 1 kilohertz to a 10 kilohertz, whatever, you can still be achieving the same 50% in both. But you're just doing it a much faster. That tends to have more switching losses, which in turn efficiency losses if your system, if your components of the system aren't rated to be able to handle such speeds. But the faster also can reduce ripple because you're now basically you're giving less time for your components to be for your inductor and capacitor to be discharging, so they're going to hold their they're going to hold their charge at a more stable level. Make sense?
So is it preferred to go with a higher frequency unless the components can't take it?
Yeah. To an extent, because yeah, you can get because that's the kind of stuff we talked about here. That is one way to increase your or decrease that voltage ripple. So if you care about that very stable voltage output, maybe it's worth it. But even when your components can handle it, by switching faster, you are going to introduce switching losses, regardless if it's capable of handling it or not. Just increasing switching frequency will increase switching losses. So it depends on kind of what you're going for. If you definitely want a very stable output, and you're willing to sacrifice a bit of that efficiency, then maybe. But increasing inductance and capacitance can do similar things. So it's two ways to achieve it. So it depends on what you're willing to prioritize.
Also, the overall solution size is smaller when you increase the frequency of switching.
Yes, because your components don't have to be able to withstand as much.
Yeah. I mean, there are
Good.
still upsides and downsides, so it's really solution dependent.
Yeah. Because if you, where did I write that? Yeah, there's two ways to go about it. You can, if you care about having a small package for this, because the trade-off is when you increase your inductance and capacitance, the physical inductor and capacitor do get larger as you go up. So if you want to keep it a small package but still be able to hit the small ripple, then yeah, you go switch it faster and just keep these values small. But yeah, it's a trade-off based off of what your design is actually going for.
Okay, makes sense.
Any final questions? Okay. Then we can call that here. We'll pick up with boost converters to start off next week then.